Hey everyone, welcome back to linear algebra. This will be part B of lecture 2, and where we'd left off previously, we had just talked through how we can use the dot product to identify the angle between two vectors. And then there were some consequences of that. Now, what we want to do next is we want to shift gears and discuss a key central concept in linear algebra, and that is the idea of orthogonality. Okay, and so let's start with a definition here, and this will be the definition of orthogonality. Let's make sure this is focused. Okay, that's good. Okay. So two vectors, x and y in Rn, are orthogonal if and only if the dot product of those vectors is equal to 0. Okay, and so what we saw just in the previous, the theorem that preceded this definition, was that x dot y is equal to 0 if and only if theta, being the angle between x and y, is equal to pi over 2, right? And so orthogonal in the pure linear algebra sense means that the vectors have a dot product of 0 when they're orthogonal. But in a geometric sense, orthogonality refers to the angle between the vectors being equal to pi over 2, or 90 degrees. And so you can think of orthogonal, and maybe you've heard of this term in other contexts. Orthogonal also can be thought of as perpendicular, right? So x and y are perpendicular to one another, right, when they're orthogonal. So that's kind of the more of the sort of geometric sense of what we mean by orthogonal. So let's look at an example here. Okay, let's consider x equal to 2 comma negative 5 and y equal to negative 10 comma negative 4. Right, so let's plot these two vectors. Okay, so this is the x-axis, and we're kind of dealing with the third and fourth quadrant here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So negative 10 and negative 4. So somewhere about here. So here's your y. Okay, and then x is 2, negative 5. So 2 over 5 down. So right about there. There's your x. And these two vectors are actually orthogonal because x dot y is 2 times negative 10 plus negative 5 times negative 4. So of course you get negative 20 plus 20 is 0. And indeed they look like they exist at right angles to one another. So this is an example of two vectors in R2 that are orthogonal. Okay, now that we can easily come up with orthogonal sets of vectors by using the standard unit vectors, right? So in R2, I and j are orthogonal. Right, remember I is equal to, these are I hat, I is 1, 0, and j is 0, 1, right? So on a grid in the plane, this would be your I, and then j is here, right? So obviously they're at right angles to one another because they're on the axes. In R3, we can extend this to ij and k, right? ij and k are all mutually orthogonal, right? Which means that any two of them are orthogonal to one another, right? So for example, I and k are orthogonal. I is 1, 0, 0. K is 0, 0, 1. Right? If I dot those together, I get 1 times 0 plus 0 times 0 plus 0 times 1. So I get 0. Okay, so now in general, standard unit vectors are going to represent an orthogonal set of vectors in general. Okay. Okay, perfect. All right. Let's talk through another theorem. We discussed previously the idea of parallel vectors. Right? We said x and y are parallel if there exists some c, constant scalar value, such that one can be made equal to the other with the addition of the scalar multiplication of c. Okay, and so another way to think about this idea of parallel is through the following theorem. We'll let x and y be non-zero vectors in Rn. Okay, x and y are parallel if and only if x dot y, okay, the dot product, is equal to plus or minus the product of the norms. Okay. All right. So, what does this mean? Well, that is basically cosine of theta needs to be equal to plus or minus 1. You know, where theta is the angle between them. Okay. Okay, so what the heck? Okay, hold on. So x and y are non-zero vectors in Rn. They're parallel if and only if the dot product of the two vectors is equal to the product of the norm of the vectors, plus or minus. Let's prove this one. Where is this one coming from? Let's prove it. Well, let's assume that x and y are parallel. Okay, let's assume that they're parallel. Then the angle between them is 0 degrees or pi degrees, or pi radians, 0 radians or pi radians. If it's 0, if the angle between them is 0, so if theta is equal to 0 radians, then cosine is equal to 1. If theta is equal to pi radians, then cosine of theta is equal to negative 1. Right? That's just trigonometry on the unit circle. Right? Remember, so if theta is 0, then this is the cosine, positive 1. If theta is pi, then this is the cosine, negative 1. Okay? So then, so what can you say? So cosine of theta is equal to plus or minus 1, which is equal to x dot y over the norm of x times the norm of y. That comes from the previous theorem. Right? Right? So what does that imply? Well, you can just do a little bit of algebra here. Look, this piece in particular, just multiply both sides of this equation here by the product of the norms, and you get plus or minus the norm of x times the norm of y is equal to x dot y. Okay. Okay. Right, and so this is just one direction of the proof. Here we assume that x and y are parallel, and we can derive that the formula is true. You could also start from the assumption that this is true and show that that implies that the angle between the two vectors is either 0 or pi, right? Basically just reverse the argument, very easy. Okay, but that's kind of the idea. It's all just sort of based on the fact that cosine can be 1 or -1, and those are the only options if the two vectors are parallel to one another. It means they lie on the same line, right? So, very good. Okay, so this kind of brings in the idea of orthogonality and kind of a slightly different way to think about two vectors being parallel. Right, now what we want to do is we want to use these ideas, this orthogonality and parallel properties here, and we want to discuss a very important idea in linear algebra, but also in the sciences, physics, engineering, etc., and that's the projection of a vector onto another vector. Okay, so that'll be up next. Let's talk through that. And we'll kind of build this idea up a little bit, try to develop some intuition first, and before we jump right into the definition. So let's let A and B be two non-zero vectors in R2. We'll start here. Okay, in R2. Okay, so I've got, let's say I've got two vectors. This one is A, and this is B. Okay, and so A and B are going to be, let's just say that they have the same initial point, and there's some angle theta between them. Okay, so we've got A and B, non-zero vectors, and we'll let theta be the angle between them. Okay. What we want to, the idea of the projection is if you think about A and B being sort of in this relationship with one another, where there's some angle between them and they have their tails are kind of at the same point, same initial point, then what you can think of is you can think of dropping a perpendicular from B down onto A, or the line that A exists on. Okay, so we can drop a perpendicular from the terminal point of B onto A. Okay, right, so drops down, and when we say perpendicular, what we mean is that that's a right angle, right? Okay. So then by the projection, okay, so here's the term, by the projection of B onto A, what do we mean? Well, we mean the vector from the initial point of A to where the dropped perpendicular meets A. Okay, so what do we mean? We mean basically this vector, starting here and extending just to here. This guy here is the projection. This is the projection of B onto A. Okay, so it's kind of a simple idea, right? But it can become complex if you let it. But if you just think of it in this simple geometric term, in this simple geometric sense, I think it's relatively straightforward. You've got a vector B and a vector A. They're joined at the tail, right? There's some angle between them, right? Now, all you want to do is drop an orthogonal from B onto A, and that implicitly defines a new vector starting at the tail of A and ending where that perpendicular intersects A, right? So here you can see the drawing, right? That's what we mean by the projection of B onto A. Okay. And it can work in the other direction too. So you may say to yourself, well, this is all nice and neat in the case of theta being like an acute angle. What happens if theta is an obtuse angle? So here's maybe my A. So let's instead say that B is up here somewhere. Right? And so in this case, here's your theta. So what is the projection here? Well, again, it's the same idea. You're going to drop a perpendicular onto the line of A, right? So the line of A means, not merely the vector A, but the straight line extending in both directions from the tail. And so that's going to implicitly define your projection. Okay, and so again, that's a right angle there. And so this is your projection of B onto A. Okay. All right, so it's the same idea. Same idea. So by using trigonometry, you can pretty easily see that when theta is between 0 and pi over 2, the vector P, and we'll call this P for now. We'll have a more elaborate name for it in a moment. P for projection. So we'll call that P for projection. Right, in this case of an obtuse angle, this is P for projection. So if theta is between 0 and pi over 2, then, so in this case, basically, then the length of the vector P is easy to deduce, right? Right, the length of P, i.e. the norm of P, is going to be equal to B times cosine of theta. Right, now do we see why that is? Let me redraw it down here so we can keep it all on one page. Right, so if I've got so there's my B, here's my P, there's theta. Right, so what I'm saying is that the length of P is equal to B times cos theta. Well, just recall from trig that the cosine of theta is equal to the adjacent side of the triangle divided by the hypotenuse, right? Right, so if this is theta, then the adjacent side is P, and the hypotenuse is B. Right, so this would be like P over B, like so, and then it's just a quick algebra trick to say that the norm of P then must be B times cos theta, right? Basically, thinking of this equation here, multiply both sides by B, right? You get what you need. Okay, so very good. So that tells us the length of P in terms of theta and B. Right, and it's similarly for the other situation, right? If, well, hold on a sec. So this tells you the length, right? This tells you the length of P, and how do we know the direction of P? Right, so this is the length, The direction of P in this case is going to be equal to, well, the direction, just take the A vector, right? Remember A is down here. P lies on A, doesn't it? The direction is just going to be the A vector. Well, you can think of the A vector as the direction, but if I want to have a unit direction vector, then I can take the A vector and divide by the norm of A, like so. Okay, and so that tells me, so now I've got the length and I've got the direction of P, right, in terms of A and B. Okay, and the angle between them. Okay, so this is in the case of theta being an acute angle. Let me summarize that. When 0 is less than or equal to theta, which is less than or equal to pi over 2, then the length of P is given by B, the norm of B, times cosine of theta. Right, and the unit direction, right, meaning just a vector that's a unit vector that tells us the direction, is given by, take the vector A and make it into a unit vector, i.e. divide by its norm. Okay, this is for when theta is an acute angle. What happens if theta, what happens when theta is greater than pi over 2, i.e. an obtuse angle? Well, so in that case, the length, right, it's going to be similar, except it's just going to be negative, isn't it? It's still going to be b times cos theta, but it's going to be in the second quadrant, so it'll be negative. And what about the direction? Well, you can still use A, right? But if A is going this way, then the vector P and theta is an acute angle, then P is going in the other direction, right? So you're going to need a negative sign on the front of the unit direction as well. Okay. And so given this, the vector P, given these two items, right, given, first this and secondarily this, we can express P as follows. Right, we can say P is equal to, well, the length of P. So here's how we could write it first in a sort of English. The length of P times, which is going to be a scalar, right? This is a scalar, times the direction, right? This is a vector, right? So you got a scalar telling you the length of P, and you got a direction, which is a vector, right? And so what are these? Well, the length of P is always going to be b cos theta, right? Which is a scalar. You got cosine theta, which is a number, and the magnitude of b, which is also a number. Okay, and then the direction of P is always going to be A divided by its norm, right? So this is a unit vector. So when you multiply it, this is the vector whose norm is 1, right? So when I multiply this direction by this magnitude, I get P 100%. Okay, and so this is the vector, that's the scalar, this is the length, that's the direction. Okay. Okay, so that's kind of the starting point here, but recall, right? Recall that we have this theorem, cosine of theta is equal to A dot B over the norm of A times the norm of B. Okay, and so what does that imply? Well, kind of taking these two pieces together, right? This piece here and this piece here, kind of taking them together. we get this. We get P is equal to, just going to rewrite this quick. Okay, so it's B, the norm of B times cos theta gets you the magnitude of P, and then it's A over the norm of A gets you the direction. Now, cosine of theta, we can see is just this, so we can plug that in. Okay, and then times A over its norm. Okay, now what happens? Well, notice here, okay, so this is an A, this is a B. All right, it's got a little sloppy. So the B's are going to cancel. Okay. And so I've got A dot B divided by, now what is this? The norm of A times the norm of A. Well, that's the norm of A squared, right? That's those two. Okay. This is a constant, and you got the vector A. Okay, so P can be expressed without the cosine, without knowing the angle, as just this formula of A in A and B. Right? So if you know A and B, you automatically know P by just calculating the dot product, squaring the norm of A, and then using that as a scalar against A. Okay. Okay, and then this is going to bring us to the following definition of the projection. Right? So this is kind of the derivation that leads to the following definition. Okay, so if A and B are vectors in Rn with A not equal to the zero vector, then the projection of B onto A is, now here's the notation we use, projection of B onto A. Not cumbersome notation or anything. So so again, this is a vector. This is the projection of B onto A. It's all what we were previously just referring to as P. Right? This is the notation for this. Okay, and that's equal to what we just saw. So A dot B divided by the norm of A squared, that's a scalar, times the vector A. All right, so that is the definition of the projection. And let's do an example where we calculate this with a real vector, So let's let A equal 4, 0, negative 3, and B equal 3, 1, negative 7. Okay. The projection of B onto A is equal to A dot B over the norm of A squared. That's a scalar times A. Okay, so A dot B, we can calculate that first. So that's 4 times 3 plus 0 times 1 plus negative 3 times negative 7. Okay, what's the norm of A? That is 16 plus 0 plus 9 square root. And then you've just got A, which I'll write like this, 4, 0, negative 3. Oh, we can't forget to square this down here. So that's how you would calculate the projection of B onto A. And so what do I get? I get 12 plus 0 plus 21 over square root of 25 squared. Okay. And so what do I get? 33 over 25 times this. Okay, and so this would be your projection vector. Now again, I mean, it's totally fine to move the scalar in to do the actual scalar multiplication. So 33 times 4 over 25 here, and then 0, and then negative 99 over 25, right? So you can do that. But notice this is just a scalar times a vector, so you're naturally going to get a vector. Okay, right? So it's a fairly easy thing to calculate, and I think the idea of it is relatively easy. It can be complicated if you let it be, but if you kind of just keep in mind that picture, right? Keep in mind the picture. You know, I've got two vectors, and one of them I drop down. That's gonna be my projection. Okay, this is B. The whole vector is A. Then this is the projection. Okay, if you can just keep this picture in your mind, then you can always reference this and you can kind of reason through these things. Okay, very good. Very good. Now, the projection vector can be used it can be used as a means to decompose B, right? So the projection vector can be used to decompose B into what we call its component vectors. Okay, it's two component vectors. Okay, so let's talk this through. So let's let A be non-zero. Okay, so notice that the projection of B onto A and B minus the projection of B onto A are orthogonal. Okay, so what do we mean by this? Let's draw a picture. So here's my A again. Here's my B. Okay, so that means this down here is the projection of B onto A. And this here, then, this vector, if you think of a third vector as lying here, this would be B minus the projection of B onto A. Okay, now these are obviously orthogonal, right, by construction, right? We created B minus projection of B onto A by dropping a perpendicular to A, right? So this has been made to be orthogonal. So these are orthogonal to one another. Okay. All right. Let's talk this out in the following theorem then. So let's let A be a non-zero vector in Rn. Okay, and let B be any vector in Rn. Okay. Then B can be decomposed into the projection of B onto A and B minus the projection of B onto A, which are orthogonal. Okay, so this is this is the statement that we just basically demonstrated, right? So we know that, you know, we've got this A vector, we've got this B vector, we can drop a perpendicular onto A to create the projection of B onto A. Now, implicitly, you could take that vector and subtract that off of B to get this drop down, this perpendicular. Now, we've been calling it a perpendicular. We've been saying that, yes, indeed, by construction, that's how we define the projection of B onto A. But how can we show that these two are orthogonal, right? We can kind of look at the picture and kind of think that through, and maybe that's enough. But let's just kind of do it algebraically. So to see that these are orthogonal, right? To see that they're orthogonal, it's important. Well, you can start kind of simplify things by noting that the projection of B onto A is parallel to A, right? So if A and B minus the projection of B onto A, if A is orthogonal to this vector, then this is also orthogonal to this vector since these two are parallel, right? Right. So if a vector is orthogonal to another vector and a third vector is parallel, then it's also got the orthogonal principle, right? But we can just use the fact that projection of B onto A is parallel to A and just do the dot product, right? So we can go like this. So here's your first vector. Let's dot that with A. Right, we can use properties of the dot product here, and we know that this is B dot A minus the projection of B onto A dot, I think of that as a vector, dot A. Okay, and that's equal to B dot A minus, and let's plug in what this actually is, and that's A dot B over the norm of A squared times A. That's this guy, and then dotted with A. Right, this whole thing. So this is just a scalar. That's the vector. Vector dot vector. Okay. And we know then that this is B dot A still over here. And this is still A dot B over the norm of A squared. Now, what is A dot A? What happens when I dot a vector with itself? That's the same as the square of the norm, right? We saw this early on, right? So you get this. And then look at what happens. These cancel, and you have B dot A minus A dot B. Well, remember the dot product is commutative, right? So B dot A equals A dot B, and so this is 0. Okay, so you get the 0. Okay, and so that means they're orthogonal. So this is sort of the algebraic demonstration that these two vectors must be 0. Okay, excellent, excellent. All right, let's do a quick example here. Let's let A equal 4, 0, negative 3, and B equal 3, 1, negative 7. Now, this is a previous exercise that we ran, and basically we calculated. Previously, we saw that the projection, we calculated this, of B onto A was equal to 33 over 25 times 4, 0, negative 3. Okay, so if I take this vector B and I project it onto A, this is the projection. So let's take this and break it down into, let's identify the orthogonal component to the projection. Okay, so the component of B that is orthogonal to A is, right? Okay, well, let me make sure this terminology is clear. So here's my B, here's my A. I drop this down. We just talked about how this is the projection of B onto A, and this is B minus the projection of B onto A. These are all vectors. Right, so when we say the component of B that is orthogonal to A, so this is B, these are called the component vectors, right? These sort of orthogonal vectors that can be used to form B. So these are the orthogonal, these are the components of B. So the component of B that is orthogonal to A is this, okay, is B minus the projection of B onto A. Okay, and so we can calculate that vector specifically in this case because we're given a real vector. So 3, 1, negative 7 minus this guy, 33 over 25 times 4, 0, negative 3. Okay, and so when we subtract vectors like this, it's really just, we just need to deal with the components, right? And so this would be like 3 minus 33 over 25 times 4, comma, 1 minus 0, comma, negative 7 minus, let's see, 33 over 25 times negative 3. We'll put that up top, like so. Right, so just taking negative 7 minus 33 over 25 times negative 3. So you can kind of write it like this if you want. And we can calculate this pretty quickly. This would be 75 minus 132 over 25. And then this is just 1 in the middle. And then this would be negative 175 minus plus 99 over 25. Okay, and what do we get here? We get negative 57 over 25, comma 1, comma negative 76 over 25. Okay. And so this is the orthogonal component that we're after. Okay, and so we know that the projection of B onto A is equal to 33 over 25 times 4, 0, negative 3. And B minus the projection of B onto A is equal to this thing, negative 57 over 25, comma 1, comma negative 76 over 25. Okay, and so we know that those two are orthogonal. Right, and so we could confirm that this is orthogonal, that this guy here is orthogonal to A by just trying to calculate the dot product quickly. So if I do that, B minus the projection of B onto A dot A, right, that's equal to negative 57 over 25, comma 1, comma negative 76 over 25. Right, so just pulling that there, dotted with 4, 0, negative 3. And let's just run this through quick. Negative 57 over 25 times 4 plus 1 times 0, so 0, plus negative 76 over 25 times negative 3. All right, we expect this to be 0. And so 4 times 57 is 228, so that's negative 228 over 25, plus, and then this is 76 times 3 is positive 228, so that'll be plus 228 over 25, and so naturally you get a 0. Right, so those two are orthogonal, as we suspected they would be because we built the projection of B onto A by dropping a perpendicular, right? And so this is that perpendicular, so naturally. Okay. All right. Very good. Okay, so I think we'll end with that. And when we come back next time, in the next lecture, we'll extend our objects of inquiry from vectors to matrices. Okay, so up next, we'll start talking about operations with matrices. Okay, that'll be the next section. All right, and I think we'll leave it at that, and we'll see you all next time. Take care.